All right, hello again. Let me start sharing the screen. Okay, so today's topic is we will continue on the submarine power cables. So submarine power cables is basically used, like from the name, which is submarine. For example, in Jordan, we have the connection between Aqaba to Taba. This is a single phase submarine. This is the side view of this. Then you look at it, you will see like here in the number in this one, you can see there is oil here, which is called oil ducts. Then when you look also in this picture, you will see there are 13 layers, like which is I mean there's a lot of number of layers there, because submarine cable we need to make sure it is being designed very well, and we don't want to see any problem or any damages because the maintenance there is at the bottom of the sea is difficult. Then again, here will you see oil ducts. What's the I mean, what's the point of using the oil ducts? Which is basically would like to provide a cooling for the cable. Why the cooling? Because as we know, when there is a current flowing in the conductor, there will be some losses. These losses goes as heat. So this core will be heated. Then we need to make sure to cool it down. How can we cool it down? Using the oil. So like the oil ducts. The other thing, which is the hollow conductor or the conductor that provide the power. Then there is inner semiconductor layer. Then there is insulation layers, outer semiconductor layer, load sheath alloy. So for the mechanical barrier to prevent moisture and insulation. There is stainless steel tapes, which is consist of two layers. Then there is metallic shield. The metallic used to protect the equipments from. Then there is bedding, and the armor is also used to prevent the mechanical strength, and also it's used for grounding as well. So we're already aware of this. The thing that's new to us, which is the oil duct number one. Then we have another bedding for the second stage, another armor for the second stage, and the outer jacket. Now there are different types of the cables here. So we can see, and this cable is called thick cable. So the thick cable, which is basically a heavy armored industrial power cable, it's very common actually. This one in Canada, and it is basically copper. It can be either copper or aluminum. Here in this picture, which is copper conductor, and the thing which is there is an insulation XLPE or um, EPR. Then there is an inner PVC jackets, and there is an outer PVC jacket. As we can see here, there are two PVC jackets, inner and outer, and the aluminum interlock armor protection, which is here. This is aluminum interlock armor, and there is also an outer PVC. The good thing about it, which is the feature, it has high mechanical strength. It is resistance to moisture, resistance to moisture, chemicals, I would say, and chemicals. Also, it can be installed without conduct. And the thing about it, why it's called thick cables, which is the key about it, armored plus flexible alternative to conduct wiring. Where should we use it? We can use it, for example, in harsh art environments. That's, I mean, the good thing about it. Now the other parts, this one, which is called shielded cable. So the shielded cable, which is basically, it comes with a metallic layer. This metallic layer is used to block the EMI and RFI, electromagnetic interference and radio frequency interference. That's what they mean by EMRI and RFI. And it can be shielded with, or the thing about it uses is to prevent noise coupling. So this most likely for the noise, while the previous one was for harsh environments, and also about the signal. Then it is, I mean, as an application in variable frequency drive of the motors. But keep in mind here, it is shielded, it's not armored. Not armored, while the previous one, there was an armor. So again, the thing about it, the difference between thick and shielded, thick, which is basically armored. Let me spell it very well. Armored, and it is armored because, or it will provide the mechanical protection or mechanical strength. And the next one, or this one, is shielded, which is, it is not armored, but there is a shield on it, and that shield will provide the electrical strength. So the thing about it, if you need to use, if you need to make sure that we have electrical strength, let's use the thick. If you need, I mean, electrical strength, use the shielded one or the thick one in case if you have harsh environment. Then the next one, concentric neutral cable. This is a conductor that has insulation either XLPE or EPR, or the other thing, which is TRXLPE, which is basically neutral wires that are wrapped concentrically. And the function of this is to be used as a neutral, As we discussed in the past, we used to say like the neutral cable, or in the previous lecture, there was a three-phase cable without a neutral. So this one comes as a neutral, or in high voltage, there is a three single-phase, cable, and the neutral cable comes alone. And again, the purpose of the neutral is for the returning current path. It's also can be used for the fault current path or grounding. And this one most likely used in the distribution, can be used in the distribution as well. The good thing about it, it will provide a uniform electric field and better fault performance. That's the thing about it. Now the next one is the paper insulated lead covered cables. So the thing about it, it can be, there's like, a conductor, there's a lead sheath for moisture barrier, which is here like lead for moisture. For moisture barrier, I would say. Then there is an oil impregnated paper insulation that's used for insulation. Um, Make sure that we make insulation very well. The advantage about it, or the good thing about it, which is this one has long lifespan, and it is excellent. It has excellent direct properties. Excellent dielectric properties. However, there is some disadvantages. So the disadvantages, the drawback, I would say, which is basically it is heavy. The weight is too much. It is difficult in installation. And the other thing about it, there is a lead here. That lead is toxic. Okay. Then the other one, there is a submarine cable. This submarine cable, keep in mind, it's different than the previous one. The thing about it, which is the previous one, there was an oil duct there, while here there is no oil duct. It depends actually in the ratings because the oil duct can handle higher currents, while this one lower currents. The thing about it, it can be again used in power or communication areas, and it is construction. The construction layer, there is conductor, there is insulation XLPE or oil filled. The other thing, which is there is a heavy steel armor. That's heavy steel armor. We need to make sure it can handle the pressure. We need to make sure it can handle water pressure and also mechanical strength, because the mechanical strength under than outside the water. Mechanical stress. I'm sorry, and the corrosion as well. Okay, then now the next thing, which is called the mining cables. So the mining cables, they are very flexible. I mean, easy to move, flexible. And the thing which is the insulation here is EPR. Then the other thing, which is some applications that we are using in underground mining, and it can be used in drag lines or in moving equipment. So the thing about it, which is used in underground mining, we need to make sure it can handle the higher temperature, can handle the like the stress, or also easy to move. So we need to make sure the material is flexible. Therefore, this one is the most flexible between them. Then the next one, which is aluminum sheath cable. So the aluminum sheath, which is basically there is an aluminum sheath here. That's the difference. Then this one is used to work as a moisture barrier. As any normal sheath, all of them like this. Mechanicals protection. Then the electromagnetic interference shielding. That's the purpose of that. And the thing which is used in underground cables in medium and high voltage systems as well. This can be used in medium voltage and high voltage as well. The aluminum sheath. Now the single core XLPE insulated cables. So as we see here, there are several pictures depending on the model. So there's aluminum core round with multi-conductor compressed inner semiconductor screening, XLPE insulation, outer semiconductor screening, semiconductive tape, copper screen, interlayer, and PVC jackets. The advantages about it, it has high thermal ratings, which make it can handle higher power, high thermal ratings, and it has lower losses, low losses, and also in addition to this, which is excellent, I would say dielectric strength. Okay, now the other thing which is like here, the application, it can be used this one as well in medium and high voltage. It's also can be used in renewable energy systems. Um, and it is very, I mean, commonly used worldwide. So this is the one, like here's like the single core, 15 kilovolt, as we see here, like this is the side of the cross section area. Then the other thing, which is the here using the 115 kilovolt, as we see, like this one is more, I mean, higher, has higher ratings. That's why you will see the diameter is, I mean, very big. Then here's like the three core. Three core means three phase, while single core means single phase. That's, I mean, how the three core has that XLP material. Um, Now, the other one, which is called paper insulated lead shielded medium. So the thing, there is no XLPE. The insulated, which is called, I mean, lead shielded. Again, we said lead shielded is good, but the thing about it, which is can impact the environment because it's very toxic. But anyway, this, I mean, will have additional shielding or metallic layer as well. Then improve the electric field control. This is, I would say, old in all the grids, while the XLPE is the common right now. This is in all the grid. And the thing is I mean, the oldest one, but again, we can see it in some old systems. Here's like how the cable on the drum, 115 kilovolt single core. You see how big it is. Now, those are the high voltage cable components, which is, we already discussed this before, almost the same, I mean, layers, just like here repeating the same thing about it. But before going here, let me summarize some concepts. Let me see if we have enough room. I need to have an empty space. I will see here. Now, let me make a small, like here is cable type, here advantage or strength, here weakness. So let me start with TIC. We mentioned that the TIC has the strength, the mechanical protection. The weakness, which is basically it's heavy. The next one, shielded cable. The strength, which is the electromagnetic interference protection or electrical protection. The weakness, no mechanical strength or not much strength. Then after that, we have concentric neutral. This is used in neutral for fault handling. And the weakness, which is complicated, complex. There is also the other one, the submarine. This is used underwater. And the good thing, which can handle extreme condition. Then the submarine, which is basically the problem about it, which is expensive. Next, after that, there is mining. So the mining, the good thing about it, which is flexible. The drawback, which is short lifetime. Then we have the aluminum sheath. The good thing about the aluminum sheath, which is the moisture barrier. The drawback is the cost. The last one, XLPE. XLPE, it's the best overall, but the problem is the cost. What I recommend to use, which one should I use? It depends on the location, depends on the challenges that you have, if it is underground, submarine, if you need to worry about the mechanical protection, etc. But what we are recommending right now, and this is the modern, is this one. So this is the standard. The standard nowadays. Okay? Now again, this is the high voltage. We already talked about this, and then we need to make sure that it can be this insulation resistance to avoid any leakage currents, high the electric strength to avoid any electrical breakdown, high mathematical strength, so it can handle the mechanical handling of the cables, non-hydroscopic, so we don't want to make sure this one is not absorbing the moisture. Um, then low cost, that's our target characteristic that we are looking for. Inflammable, so this will not be heated and impacted by the temperature. And the other thing we need to make sure it's not affected by the acid or alkalis to avoid any chemical actions and has low permittivity. The thing about it, there is no one insulation material that can handle all of these characteristics. I mean, we have how many characteristics that we have? 1, 2, 3, 4, 5, 6, 7, 8. I mean, in order to satisfy all of these 8 characteristics at once, there is no way. While what we need to do is try to take some factors, the most important factors, and keep the others. Therefore, the main insulation materials actually is polymers. But after that, we modify, we make an XLPE. So, I mean, this can be extracted from the natural resources as paper, wrapper, or it can be manufactured by the process of polymerizations, and it can be called compounds. Then the paper insulated cables were strictly the first type of polymer used since it's been readily available from natural resources. Paper is derived from wood, as we know, wood pulp, and which is natural polymer comprised with the cellulose. And the main goal of the impregnation to ensure the sufficient cooling and overcome overheat that could be generated over load conditions to the cable. Therefore, we need to make sure it may that must have the following things, which is low permittivity, this is the insulation material, and low capacitance that reduce the value of charging currents, and high insulation resistance. That's what we need to think about. So the impregnated paper, the good thing about it, which it has high dielectric strength, which is the maximum electric the maximum electric field that can tolerate without breaking down, which is again I mean, that's the definition of the dielectric strength. The maximum electric field that the dielectric can be tolerate or withstand without breaking down. The main disadvantage of this paper is that it absorbs moisture regardless of the impregnation with suitable compounds. So, which is absorbing moisture. The paper insulated cables are usually used in routes where it has few joints. So when there is a joint, it's also be impacted. That's one of the other disadvantages. Then we need to make sure that it will not absorb moisture and decrease the lifetime of the cable. If this problem continues, which is there are many joints or, I mean, there is absorbing moisture, it will impact the lifetime of it. The oil impregnated paper cable of three, here was the impregnated, now it's oil impregnated. Three conductor were used extensively, so the built cable was found to susceptible to high partial discharge. Then the thing about it, the operating voltage range to 35 kilovolts due to non-uniform distribution to the cable construction. The other thing, which is the rubber which is obtained as we know from the trees that can the relative permittivity dielectric constant between 2 to 3. That's the dielectric constant. Although pure rubber has a reasonable high insulation resistance, but suffer from the disadvantages. So the pure rubber has these the following disadvantages that prevent us from using the pure rubber. The rubber absorbs moisture, which is again absorbing moisture will decrease the lifetime of the underground cable, which is something that. Then the maximum operating temperature is low. This is the disadvantage for it. Then the soft and liable damage due to the rough handling and edges when exposed to light. Therefore, pure rubber is not used as an insulation material, but also some impurities can be added by adding some impurities to the polymer, to the rubber or polymer. This can be added to the pure rubber to improve the insulation properties and its resistance to mechanical conditions. Vulcanized rubber, which is prepared by mixing pure rubber with mineral matters such as zinc oxide or red lead, etc., and 3.5 of sulfur. The compounds that's in the sheath, we need to make sure the rubber compound is applied to the conductor and it's heated up till 150 Celsius. This process will produce a vulcanized rubber. Again, the vulcanized rubber is take the normal rubber and apply and heat it up to 150 degrees. Then let it, cooling down. Once we see that it will provide a vulcanized rubber, the vulcanized rubber has the following disadvantages. The following advantages, I mean. So the first one, greater mechanical strength. Second one, higher breakdown resistance and insulation. Third one, non-hygroscopic. Then number 4, which is more stable than the pure rubber. That's a good thing about it, such that the mechanical, electrical properties do not change with them. Vulcanized rubber is usually used for low and moderate voltage levels, which is low and medium voltage, while it's not, commonly used in high voltage. Polyolefin insulated materials. So there are many types of polymers that can be used as insulation materials under each material different from from the other one in its electrical properties or in the mechanical properties in the evaluated between the difference of the properties in order to produce optimum insulation material with the acceptable prices. There are different types of polyolefin materials. There is PVC, which is polyvinyl chloride. This is very common. We have heard about it a lot. This is insulation material is the synthetic compound, which is obtained from the polymerization of the acetylene, and it is in the form of the white powder. For obtaining this material as a cable insulation, it is mixed with a certain material known as plasticarizers, which are liquid with high boiling points, boiling at very high temperature. Then plasticizers form gel and rendering the material plastic over the desired range of temperature. The main advantages of the PVC has more attractive appearance. That's a good thing about it. Lightweight and easy to handle. Also, it's non-hygroscopic and therefore it's unaffected by the increase of the moisture. That's a great thing of the PVC. Then PVC is flame retardant and has a greater ability to stand with the mechanical damage than paper. So which is can handle more mechanical and it can be, which is again flame retardant. So this the PVC is more suitable for hazard situation, such as in mines or quarries. The disadvantage of the PVC is the maximum permissible operating temperature is 70 Celsius compared with 80 Celsius for the paper. And in addition, the special plasticizers and stabilizers, PVC can operate up to 80, 60 degrees after adding plasticizers and stabilizers. Polythene PE, polyethylene PE. PE is a straight chain of polymer produced from the polymerization process of ethylene gas, which is which will eventually produce a thermoplastic material. This is process is accomplished by applying a certain pressure. This pressure could be high or could be low depending on the settings. The high pressure process produce low density polyethylene. The high density polyethylene produce low pressures. That's thing that which is the opposite of each other. High density PE is stiffer, harder, and more breathable than low density polyethylene, which is high density PE has the ability to resist chemicals and moistures and flexible at low temperature. Again, polyethylene, the main advantage of polyethylene are related to the high dielectric resistance, low power factor, high dielectric strength, low thermal resistance, ability to withstand with reasonable. It can operate at the maximum conductor temperature above the 70 degrees Celsius due to higher molecular weights of high density polyethylene because it has a higher molecular weight. They are commonly preferred to the high molecular weight aids, which is called HMWPE cables. Cross-linked polyethylene, XLPE, this is very common, the most commonly used. As we mentioned earlier, like XLPE cables, the most commonly used. So cross-linking means the polyethylene chains are linked together. In a sense, XLPE can be considered to be a branch of polyethylene where the branch is connected to the different PE chain instead of just hanging loose. Cross linking parts where certain quite desirable properties to the PE form cables on perspectives which allow the polymer to maintain its form stability temperature. Process causes polyethylene to change because of the cross-linking to change over from a thermoplastic material to a thermosetting material with a considerable improvements in both mechanical and electrical properties. Because of this thermosets character, XLPE maintain its mechanical properties when exposed to the temperature, which was caused PE melts while lose shape and flow. The cross-linking XLPE process is achieved by introducing agents such as organic peroxide, which is also that's the other thing, which is um, Decomel, which usually used as the cross-linking agents. In the past, XLPE power cables were steam cured with the considerable moisture in the insulation. After that, the dry curing process was used. That was in the past. Most XLPE cable are now produced using this method. It was definitely established that the use of the dry curing process produces lower number of microavoids. That's many or that may or may not be complicated in the water tree growth. Water trees. Now, water trees, which is basically the degradation of the cable, degradation phenomenon, creating structure in polymer insulated under the influence. This is used again in polymer insulated under the influence of the moisture. Because of the moisture, it will start, impacting the cable, causing water tree, and which is the influence of the moisture and the electric field. So there'll be a small leakage. So, however, under those circumstances, electric treeing and complete breakdown may occur also depending on the precise condition. Electrical treeing and breakdown are distinguished from the water treeing. For this reason, more specific definition is needed. So, what's water tree? What's the definition of the water tree? Which is water tree are the degradation structure of the polymer that are permanent, cannot be fixed, and have grown due to the least humidity, at least humidity and electric field. So there will be some leakage on it, have a lower electrical strength than the original polymer, which is the electrical strength can be broken down. Uh, Another definition, those are small discrete voids separated by the insulation. Water trees develop slowly, growing over the period of months and years. Much less electrical stress is needed to cause the water tree. So it doesn't meet a high electrical strength. A small electrical strength stress can cause water trees. Water trees actually looks like fans, blooms, or bushes, as the name indicates that water trees need moisture to grow. Without moisture, water tree will be, very low. Water that enters the dielectric accumulate in specific areas, non-crystalline regions, and causes localized degradation voids, which is basically also voice contamination. Temperatures and voltage stress are influenced by the rate of the growth. This is how water tree looks like. This is the insulation XLPE, and here is like the conductor. So you can see it caused some permanent damage here. And that permanent damage happens because of the humidity that can make a permanent damage. So, which is called water tree, which create like here impact the electromagnetic interference and the electrical connection as well. So the formation of the water tree does not necessarily mean the cable will fail. It means it's about to fail. It's just like a warning flag. So water tree can even bridge to the entire dielectric without immediate failure. Well, it's accumulative. It is cumulative. Then failure occurs when the water tree converts to be electrical tree. That's the thing. So, once it's water tree, it is not, harmful. It is, it can make, impacts on the long term. It will not do the immediate fault or immediate fail. The immediate fault or fail will happen when the water tree converts to be electrical tree. Then they can literally pour a tunnel from one void to other, contaminated to the next. Impulses and DC voltages can trigger electrical treeing in a cable that's heavily water treated. The electrical trees, which is basically the more advanced, which is comes after water tree. So the early stages it will be water tree. Then once it starts being harmful, then it will be called electrical trees. Electrical trees will cause the immediate failure. So electrical fields can be developed from high voltage or electrical stress. So it can be developed like this, or it can be originally was water tree, then it was cumulative to form the electrical tree. So this stress creates like the partial discharge that's away from the insulation. Electrical trees can grow fast. That's the problem. fast falling cable within hours or days. Three retrograded XLPE, which is called TRXLPE, that's the shortcut of it. So for further remarkable advantages, they were to made to control the water treatment by introducing the dry cleaning process, super smooth and clean semiconductor shielded and trees terminated cross-linked polyethylene. Various attempts have been made to develop additive with tree retrograded properties to prevent or reduce water tree phenomenon. Then it was like there was like a water tree inhabitants. Then the effects of it can diminish with time. Retardant ethylene vinyl acetate EVA that was used in XLPE insulated cables, but also tended to lose its effectiveness over the prolonged time under low voltage stress. That's something that we need to avoid under voltage stress. Okay, so ethylene propylene wrapper, which is called EPR. Some of the insulation materials are based on EPR. EPR insulated cables having fillers that contain as much as high 50% fillers, clay fillers, up to 50%. Then they are usually preferred over XLPE insulated cables where they have mechanical flexibility of the prime concern, which is suffer from the poor oil and flame resistance, and it's also susceptible degradation by partial discharge and treeing. The disadvantage, which is basically the overall cost. Installation thickness determination of power cables. So any analytical expression derived from the calculation, we need to follow the IEC standards to do that. So which is commonly recognized that the ionization in voids is the critical factor in governing the insulation. So we need to make sure that there will be no insulation in the voids, so which impact the insulation size and also can impact the solid dielectric power cables. This is because extruded dielectric are more prone to damage from partial discharge. So that's something very important statement. Extruded dielectric are more prone to damage from the partial discharge than paper insulated power cables. Okay. Insulated thickness determination, again, the analysis regarding the discharge of inception voltage of the cable depending on the shape, depending on the size and the location of the void within the cable insulation. Using the consideration that the voltage rating of a cable must sit below than that this must sit the voltage rating below than the discharging inception voltage of the cable, which is assumed that a single void exists in a cable. Therefore, the fundamental consideration for the determination of the voltage rating of the single is preferred as a single SVD, which is single void discharge method. Insulation resistance for a single core cable, the insulation resistance between the conductor and the outer sheet is given by the following. Okay, let's keep going. Now here it is like this is the cable cross section. Then we need to calculate the resistance. The resistance, as we know, rho times L over the cross section area, rho times L over A. So here is rho L, which is basically we denoted by delta X, and the cross section area, which is 2 pi times X times L. Or I would say like 2 pi. Is there X here? Yes, times XL. Then where is like L is the length of the cable, rho is the resistivity, delta X is the difference in the, I would say, which is the thickness, while X from the center toward the distance. Then we can say like the resistance can be calculated using this formula. And keep in mind this formula, which is basically in ohms, the units in mega ohms. The other thing, keep in mind L prime can be substituted by the length of the cables. Capacitance, single core cable. Assume we have a single core. Again, single core means single phase. The capacitance, as we know, this is positive and the other part is negative. So there should be a capacitance from here to here. Then how can we calculate it? We can use Gauss law, and then basically Q equals the integral of d ds, then the surface integral, then it will be d times 2 pi x L times L. Then we can calculate d, which will be q over 2 pi times x. Then the electric stress, zeta equal d divided by epsilon, which is q divided by 2 pi epsilon naught epsilon r x, which will be 18 times 10 power 9 divided by epsilon r times x. Now here's like the capacitance, then it's for the capacitance, the way that I like is the microfarad per meter. Don't need to worry about the miles. Just worry about the microfarad per meter. That's how we can calculate the capacitance inside the single core, which is there is one capacitor. Now, how about if there are three cores? If there are three cores, then you should expect to see two types of the capacitance. The first capacitance between the cores themselves, then the other capacitance between the conductor and the ground. So this one we can call it Cm, the other one is called Cs. This is Cs, 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 while this one is Cm, Cm, Cm. Now this is the overall formula about the calculating this is in terms of epsilon, T, and D, and tau. Once we know them, then we can just substitute them, such that T is the thickness of the belt insulation, tau is the thickness of the conductor insulation, D the diameter of the conductor, epsilon R is the dielectric constants. Now, how about if we need to measure the capacitance of three-phase core? The first thing that we need to do is basically try to make a test to calculate. We have two unknowns, Cs and C. So let's do the first test by shorting the three conductors. Then we have and measure using the bridge, measure the CS or measure the equivalence value. Then we realize all of them they are shorted. This between positive to ground, positive to ground, positive to ground. Then therefore we can say all of them they are in series. So as a result, we can say C equals 3 times Cm. And 3 times CS, I would say. This is called, we call it CM1 because we have the measurement number 1. Then that's it. The second thing is, let's short the phases. I mean, the previous one we did, which is called it like three-phase connected. While we keep the others the same. Then here, we connect each phase to the ground. Then here, the measured value that we can calculate, which is basically 2C times plus CS. So as a result, this is the formula that you need to use. You can write it in your note sheets because this is a very important formula. Then you can solve the question using this. This is to calculate the capacitance for C. Now the next thing, how about to calculate CS? To calculate CS, we can say this is or CO or CS, whatever you're gonna call it. 3 divided by 2, Cm2 minus 1 over 6 Cm1. So in summary, we can say we can calculate CO, which is 3 divided by 2, Cm2 minus 1 over 6 Cm1. Then the other one, which is C,
alone, which equals to be Cm2 minus Cs divided by 2, or 3Cm2 minus 6Cm1 divided by 6, which is, I believe it's the same as this one. So when you look at it, here is the first one, and the second part, the second equation is this one. So we have two equations. C naught equals Cs plus 3Cm. So once we are familiar with Cs plus 3C, which is basically 1 divided by 3 Cm1 plus 3, I would say Cm2 minus Cm1 divided by 6. Then it will cause, then how can we solve it? Then the space factor, basically you will see here, this area is not used. Which is here, the space factor is high. While here, we change the shape a little bit to improve the fill factor. Here, the fill factor is high. That's the difference between them. The SFD, single void discharge method, the SFD method states that the voltage rating of the solid cable must be below the minimum discharge inception of the voltage Vm. So how to calculate Vm? Vm basically will be alpha times R divided by KT ln R as divided by RC. So alpha is basically in the Bashkin curve, which is 0.34 kilovolts, while the rest equipment should be given like dt is the thickness of the cavity, R is the distance from the conductor center to the cavity, RC and RS are the radio cable conductor, and the over the insulation as shown in this figure. So that's how we can calculate RC and RS, that's how where they're located. SVD, the K coefficient is expressing the field enhancement within the cavity, which is basically depending on the material. So according to this example, to the previous one, related to the some numbers. Let's see where are we. Then we can say K equals 3 epsilon R divided by 1 plus 2 epsilon R. Epsilon R is related to the material. We call again the electric constants. So K overall is called the coefficient expression to the field enhancements within the cavity. Single void discharge method SVD, which is here the size of the voids in the polymetric cables spans a wide range, which will gradually enlarge during the service. That's good. However, for a freshly extruded cables, the maximum size of the voids Tmax can be defined as the 59 micrometer. This size has been specific in some current standards and specifications. The VM, or is it, I believe it's here, yeah, the VM overall. The VM depends on the size and location of the void, since the distribution of voids in a polymer is random. The worst case assumption that a void of maximum size is located in the conductor still has to be made. So the voltage VM for the polymer cables can be calculated as VM equal alpha RC divided by KT max ln RS divided by RC. Then the minimum installation thickness can be given as this, RS minus RC. Then we can calculate it here, such that VP is the same as VM prime, which is the peak value of the operating power between the conductor and the size. All right. Let me take 1 minute break. Then we'll continue. Just give me a break, 1 minute.
Okay, I'm back. Um, Now let's take an example about the SVD method. So the thing here, we need to calculate the insulation thickness for a 33 kilovolts, um, given that we have a 240 single core power cable, 240 millimeter square, which is constructed from XLPE and has a maximum void thickness, which is 50 micrometers, and the XLPE given the dielectric constant 2.5, alpha equal 0.34 kilovolts. So to calculate this, the first thing, let's calculate RC first, because as we see here in this picture, there is RC, TM, and RS. So let's calculate RC first. Where is it? Here, which is the square root of 240 divided by pi, then it will be 8.75 millimeter. Then when we calculate K, which is again 3 times epsilon over 1 plus 2 epsilon, then it will be 1.25. Then VP, which is basically the voltage square root of 2 divided by 3, then it will be 27. Then TM equals 6.7. So just like applying this formula, we'll apply this and this to get the answer, 6.7. This is the maximum thickness, or the thickness. So again, look at this picture, then you have a clue that RC, which is radius of the conductor. TM, which is, I would say, like the length of insulation. RS, I mean radius of the cable. Okay, let's keep going. Then here, let's do the same, but instead of 33 kilovolt, it will be 132 kilovolts and 1000 millimeter square. Then we can see RC is different here, around 18 millimeter square. RK is the same, assuming the same insulation material. Then VP will be different because the voltage is different nowadays. Then TM will be, after we calculate it, will be 16.9 millimeter square, I'm sorry, millimeter. Insulation resistance in a single core cable. Now, we need to calculate the resistance for that. Now, we just calculated before the thickness. Now, how about the resistance? To calculate the resistance, we can do the integral. So here is like by taking delta or dr, then we can do the integral and apply the formula. So, I mean, what we need to do is basically you can take this conclusion, use this. This is the resistance. Rho is the resistivity, while L is the length. Then R2 and R1 are basically R2 is the radius of, or R1 is the radius of the conductor. R2 is the radius of the cable. R1 radius of the conductor. R2 is the radius of the cable. Okay. Then here we can calculate R using directly this formula, rho over 2 pi L ln R2 divided by R1. Let's look at this one. Assume determine the insulation resistance of a single core that has the length 3 kilometers and the radius 12.5 millimeter, insulation thickness 1 centimeter, and insulation has the resistivity 5 times 10 power 12 ohms per meter. So we can say the conductor size, which is, as we said, like R1, 12.5 millimeters, R2, which is R2 is the, I would say, cable radius. So the cable radius will equal to the core radius or conductor radius
plus insulation thickness. So the core radius, which is we calculated as 12, or it's already been given as 12.5, the insulation, which is given as 1 centimeter, 1 centimeter, which is actually 10 millimeter. So in terms of millimeters, about 10, it will be 22.5 millimeters. Or if you want to write it in centimeters, 2.25 centimeters, whatever you like. Then after that, we can substitute them directly. So rho 5 times 10 power 12, which is given here. Then 2 pi times L. L is the length, which is given 3,000 meters or 3 kilometers. Then ln, this is R2 divided by R1. After substituting, it will be 156 megaohm. Now, insulation resistance of a single core cable, again, this is the formula that we have. Then if we have the length 3,000 meters, or I would say, let me see here, yeah, this, which is 3,000. Again, this is the picture for the things. Then capacitance in a single core, we can calculate it according to the IEC standards, where it is like R1 equals D times C divided by 2, R2 equals DI divided by 2. This is the radius. What do I mean by DC and 2 and DI? So again, R1, which is related to, let me rewrite it here. Or it's already been given here. R1 radius of the conductor. Now, how about the diameter? Diameter, which is basically like this one. Uh-oh. So this is conductor DC, diameter of the conductor, which is equals 2 times R1. DC equals 2 times R1. The other thing, which is R2, which is the radius of the cable itself. How about or we'll call it DI, then which is 2 times R2. This is the diameter, the cable. Like this, from here to here is D. Then to calculate the electric field, Q over 2 pi epsilon naught, epsilon R times R. That's, we already know this formula for the electric field on a point. Then the voltage difference between the core and the metallic, the voltage difference between the core and the metallic, which is the diameter, or between integral between R1 to R2. Let me go back to this picture. We need to calculate this, to calculate the voltage across this area by taking the whole around the circle, this area. Then we take we say the integral from R1 to R2, or in other words, we can say, because as we know, the R1 equals DC, or DC equals 2 times R1, therefore R1 will be DC divided by 2, the diameter of the conductor divided by 2, and the diameter here of the cable divided by 2. That's why we see here divided by 2, divided by 2. Then here the energy, or I would say like electromagnetic field, then dr. When we substituted this and do the integral, this is the net value or the final value. To calculate the capacitance, as we know, Q equals times CV, therefore C will be Q by V. Okay? Then Q by V, we already have the voltage equation here. We can substitute it. This is this formula. Q and Q cancel each other. this will move to the other, to the denominator, yes. From the denominator to the numerator, I mean. That's what I said. Then 2 pi epsilon naught epsilon r divided by ln di divided by dc. Then we can just substitute epsilon r as 1 over 4 pi times 10 power negative 9. I believe 1 over 36 pi. Then you can say 36 by 36 and 2. This seems to be 18. Pi with pi cancel each other. Then here we substitute it's epsilon naught. Then it will be times epsilon r divided by 18 ln d divided by dc. Then the answer will be in farad per meter. That's the thing that you need to keep in mind. Then this is how we can calculate the dielectric strength. Again, this is the electric field by any points r. Then after that, we can calculate the capacitance overall, which is V divided by R ln di by dc. Then in order to calculate the maximum electric field, where is because as we know, it is bounded between dc and di. At dc, it will be maximum. At di will be minimum. Just substitutes R equals dc, or I would say like dc divided by 2. Or dc divided by 2. This is the max. Substitute R equals di divided by 2. This is the minimum. That's that thing you need to keep in mind. Okay, so let me stop here at the economical diameter of the conductor. Then we will continue, inshallah, next lecture.